Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so start the next session. We got two talks coming up. First is Kevin Bowers. I'm going to be talking about cloudy without a chance of data loss. Almost misspoke on that. Implementation. So I guess we'll be seeing lots of source code through this.
And actually no source code, but sort of follow-on work to Ari's talk this morning. He made everything look nice and rosy and all happy. And the problem is when you get to implementing some of it, there's a few more challenges than you might expect. So considering where we are, I'm going to skip right past the motivation part and jump right into proofs of retrievability. So sorry for the context switch. We just did PDPs. Now we're jumping back to PORs. So try to bear with me. So first, a little setup here. This is sort of how we think about the world when we design PORs and Hail, and even some part for Raft. You've got a user here, Alice. She's got a collection of photos, and she's going to just line those up and make one massive file out of them. And for certain applications, we might split this file into, uniquely or evenly sized pieces. So Ari talked about a proof of retrievability where I can now take this file, I do some encoding on it, and I store it in the cloud. But what he failed to mention was how do you do that encoding piece? What does that look like? And so I'm going to quickly walk through what that encoding looks like. So this is an adversarial encoding, and the reason we have to worry about the encoding here is we're going to take this file that we want to last forever, and we're going to give it to the people we trust the least. So this file needs to be resilient to anything they can try to do to it. So the first thing we have to do is we actually have to permute the file. We have to rearrange it. And the reason for this is because the files are so big, we can't compute error correcting information over the entire thing in one pass. So we're going to have to do striping. We're going to have to break it up into pieces and do an error correcting code over that, and then take the next piece. But if I just did straight pieces, it's easy to identify where the piece boundaries are and utilize that structure to break the file. So I actually have to permute the file before I do my error correcting. Now I can do my error correcting over what is essentially a randomly rearranged file. I can now put the file back in the original order, and this is nice because now when I go to download it, it's sitting there in the order that I expect. But the error correcting information is computed over a random ordering. And now to make it even more complicated, I have to actually rearrange and encrypt that error correcting information. And this is again to hide the structure from the people who are going to be storing this file so they can't utilize it. And then we do our pre-computation and encryption of responses. So we take a selection of blocks, compute an aggregation of those. That gets stored at the server, and those get encrypted as well. So that's question.
So the original papers, any error correcting code will work. So you're saying that it's incorrect, that you need to have this random permutation? Sorry, I just missed the point why you need to rearrange.
So we can use any error correcting code. The problem is they're all essentially linear codes, and so there's structure that's easily pulled out of those. And so if I just broke the file up into pieces and did my correction, then I could easily map the piece here and its error correcting information out on the end. And I could just knock out both of those and lose the whole file. Essentially what we're worried about is the adversary, the person we're going to store this file with, being able to take out very small pieces of the file and yet render the whole thing unrecoverable.
But he can always do it, right? PR doesn't protect.
He can delete a large piece of the file, but that we can detect.
Right.
So that's the design of a PR. Any large corruption is detectable, but tiny corruptions are not.
So you want to avoid computing the error correcting code of the entire file in one block?
That's basically impossible. There's no error correcting code that can do that anywhere close to efficiently.
Oh, I see. So that's
So we've got to do it in small pieces.
piece
And now we've got to hide where those pieces lie. Thank you.
You want to do essentially efficient, assuming that you can only do error correction on small blocks, how to do encoding of a large file.
Exactly. Without letting that structure out in the open. So the first challenge this raises is, okay, so what is this permutation? How do I rearrange a file? Well, it's a pseudo-random permutation over some medium-sized domain, for whatever that means. And specifically, the domain is the number of blocks in our file. So how big is our file? That also implies that we need a variable length PRP here. Problem is the smallest block ciphers that we know of that we could build this out of run over 64-bit values. So if we translate that to, each byte is a block, we're talking about a 16 exabyte file. So we're going to have to do something to shrink this block cipher to the domain that we're looking for. There are a couple of techniques for doing this. The first is known as ordinal sorting. So take your numbers, pass them through your PRP, get some set of outputs, and then sort those outputs. So what happens here is I've taken my numbers, I've generated their outputs, I sort the outputs into their rank order, and then what happens here is 1 mapped to 3 through my PRP, but that becomes the second element in my ordered set. So my mapping is from 1 to 2. And you can follow that through for the others. So this last column here, this is the PRP that I could use over a smaller domain. Another option is what's known as cycle walking. So now you pass your numbers or your input through a PRP, and you see whether or not they land back in the domain. And if they don't, you do it again.
Sorry, what approximate size would you say? Something smaller than 64 bits?
Yeah, so 64 bits gives you like 16 exabytes.
Right.
We're looking at files that are giga to terabytes probably.
So you're trying to define a PRP on a particular...
So we're trying to find a PRP...
What's K here, I guess, is my question.
Exactly. So K is something like 2 to the 30th, maybe 2 to the 40th.
Okay.
And then, again, this changes depending on what file we're encoding. Yeah, so it's got to be variable. And so here, basically, if your mapping doesn't land in the domain you're looking for, just map it again until you get something that does. So ordinal sorting is feasible up to about 2 to the 25th. Beyond that, memory and space just get too expensive to do. And cycle walking, so this sort of builds up from 0. Cycle walking sort of works down from the original size. And it's only feasible to in over 500. So you've got your 64 bits. You can sort of think about what that would look like. Basically gets you down to a 32 petabyte file. And unfortunately, there's a pretty big gap between the two. And most of the files that we'd be thinking about probably land in that gap. So the solution turns out to be a Feistel construction. And this is very similar to the work on format-based encryption. They use a very similar construction to do format-preserving encryption, excuse me. So it'll work for anything of a power of 2, and then you can use the cycle walking to get you down to your exact domain that you're looking for. There is a minimal loss in security. But in the way our PRP actually gets used, there's no attack vector for that weakness. So getting less than perfect security is acceptable. This is what a Feistel construction looks like for those of you who are interested. Basically, you take your input, you split it into 2, and you do a bunch of recombinations and shifts. Explained through, well, look, I did get you some pseudocode. And what we found is that you can get good enough security bounds using a 6-round implementation. So 6 splits, recombinations, permutes. So that each section here is 1 round. So if you can do 6 of those, you get good enough security.
Are you measuring that in some manner, or is that just a...
So yeah, so there is a reduction based on the number of rounds to the indistinguishability, and you can get acceptable for our application with 6. In fact, the format preserving encryption uses even fewer rounds because they have a slightly weaker model. They actually redefine security primitives because they're not comparing to PRPs. Yeah, work by Luby and follow-on work by Rogaway, I believe. It's been a while.
So the 6-round proof you're plotting is from Patron.
Thank you.
And the format preserving encrypted paper was, yeah, Rogaway, and then also Galari myself.
Yes. Thank you. So the second challenge with doing POR encoding is that we're using very large files that aren't going to fit in memory. And the rotational drives that they're sitting on are terrible at random access. So I can't go pull out pieces of the file and do my encoding. So I'm going to have to do my encoding incrementally. I'm going to have to read my data sequentially. So if these are the pieces I need to compute one error correcting symbol, what I'm going to have to do, I can't do that because only a third of the file fits in memory. So I pull that third into memory using sequential reading from the disk, and I take some intermediate value. In this case, I can just take that one block. As I read more of the file into memory, I pull in the blocks that I need from there as well, and now I've got some intermediate value. This is some running computation that's going to let me eventually compute the error correcting symbol that I need. And lastly, I pull in the last one and complete the computation, and then this can be appended. And I've actually got to do that for every single error correcting symbol all in one single pass through the file, because otherwise the efficiency or the performance suffers so bad that it's not worth doing any of this. So in fact, you get to the point where you run out of temporary storage space on the server or wherever you're doing your encoding at about 12 gigabytes. So if you have a 12 gigabyte file, you've got to keep so much temporary information to be able to compute those that you're still running out of memory on some standard desktop machine with maybe 2 gigs of RAM. So that becomes a limit, and then you've got to think about doing things like splitting up your file into 12 gigabyte chunks or whatever. So that's certainly a challenge that we faced in implementing a proof of retrievability. Moving on to Hail. Quick little reminder of what this looks like. You've got your file, you've got your encoding. You split that across your 3 providers. And then you compute some extra information for your additional providers. And I already talked about this morning in a little bit less detail. The concern here again is that the order you do this stuff matters drastically. Because again, we've got to read these off of disk. So the first 3 blocks actually all show up on the same disk in sequential order. So it's not too bad to compute what's going to go on providers 4 and 5. And in fact, I'm going to do that all the way down. And then I'm actually going to write that out to disk for all of them and read in each file separately to compute these. If I were to do it in the opposite order, I would incur all sorts of random access to disk, and basically it becomes impossible to do in any sort of realistic time. This, as it is, takes a couple of minutes for a several gigabyte file, and to do it in the other order would be on the order of days. So now let's jump lastly to RAFT, and this is sort of our most recent work. And what you'll notice is a lot of the issues we've come across is all based on this very limited device. We're using rotational drives. That's the standard today. Solid state is becoming more and more popular, but large data centers use rotational drives. They have a seek delay when reading or writing. That's on the order of about 4 milliseconds. They have limited throughput, though it's not bad. And they're good at sequential access. So if things are read in order, they do a good job of that. They are absolutely terrible at random access. And all of these limitations are sort of covered up by several layers of caching. So there's caching that happens on the drive itself. There's caching that happens in the operating system. And these actually lead to a challenge in RAFT. So for example, if you were to pull 50 random blocks from a rotational drive of varying sizes, you would see time to do that basically follows these curves. And what's happening here is there are some caching effects that basically make everything up to 64 kilobytes look exactly the same. So the caching on the drive and in the operating system and anywhere else that caching is happening sort of limit the design choices that we can make. So whether we choose a 512 byte block or a 64 kilobyte block isn't going to matter. And that affects how you can do the testing for RAFT. So let's jump into the testing for RAFT. Unlike Ari, I'm not going to give you a little happy fraternity and pizza example. This is actually going to be how RAFT actually works. So for those of you who didn't get the analogy this morning, here are the details. So again, we do some encoding of the file, and we upload this to our cloud provider. The cloud provider is then going to store that file across a number of drives. And the idea is each of these drives are independent devices. I can address them independently. I can get data back from them independently. So I can specify one block on each and read those back in 1 unit time, whatever that unit time is. And in fact, I can do this as many times as I want, and I can do it non-interactively. So if I take the output that I got back, if I take those blocks, I hash them all together, and use that hash to create some indices for my next block, I can do this in some sort of lockstep protocol. So each round, I'm going to pull one block from each disk, compute the next block I need to go get, pull those blocks, again, in one time step, and sort of continue this for as many time steps as I need. And I might have extra time steps here because I need to account for network variability or other sources of variability. We'll get into those in just a minute. The final set of blocks can then be returned to our user. Alice can check that those are correct. And the other thing that she checks, obviously, is the time. Did they come back quickly enough? And this time is important because, remember, each read takes one time of 1. If we have fewer drives than we're promised, so now we're only using 3 drives, whereas we were promised 4. If we ask for 4 blocks, there's got to be a collision on at least one of the drives. So one of the drives is going to have to do a double read. And so we can do the first 3 reads all in one time. But that second drive, the drive where the collision happened, is going to take an additional time step. And again, we can magnify this by running this protocol in lockstep over a number of rounds. So obviously now it's taken twice as long to get these back. And even if there's significant variability in the network, Alice can get these back. They'll be correct, but the time will be unacceptable. It will have taken too long, even regardless of network variability, because we can have this extended protocol that goes through numerous rounds. Well, so let's talk about sources of variability, because those are going to play a big role here. One source of variability is the read time from disk. So I said disk access time, disk seek time was around 4 milliseconds. Well, so then you add in the time to actually read the data from the disk, and you get a distribution that looks something like this. If the disk head happens to be sitting at the right spot, you can do it very, very quickly. If your average case, you're somewhere around 6.5, 7 milliseconds, maybe you have to wait for a whole disk rotation after you've moved your disk head, in which case you end up here. And this graph actually continues to go out because there can be misreads and rereads and data that got remapped on the drive to other locations in the drive. So there are a whole host of factors that make this not a perfect picture.
Is this with caching turned off?
No, this is with caching. So this is exactly the system you would expect it to be running on And so testing as close as we can to real world. Well, so why is that a problem? Here we are again back in our 3-drive model, where the server has promised us that our data is being striped across 4 drives. Well, with caching, it's possible that they all read at different rates. And in fact, I can do a double read before one of my single reads finishes. And that becomes problematic because now the server can cheat by, maybe he's got 2 desktop class drives and 1 enterprise class drive. And the odds of him being able to do that double read increase significantly and do it without being detected. So we've done some tests over drives and then sort of simulated that out to a full-scale system. And what we found is that you have to increase the number of steps, obviously, to detect the cheating. And we sort of get to the point at 17 drives, or at 17 steps, rather, sort of the adversary's chance of fooling you becomes essentially negligible. So what's happening here is, what I've graphed is the difference between the best adversarial response time over 500 runs and the worst expected case or correct server over 500 runs. So there's a distribution for correct and a distribution for incorrect, and I'm graphing their 2 closest points, the min and the max. And what you see is if at the point where you get up to 50 steps in your protocol, there's an 87 millisecond separation. If we look at that point in a little more detail, this is the actual distribution you get of 500 runs. So your honest server that's using 5 drives will give you this distribution, and your cheating server will give you that. So at 50 steps, you have an 87 millisecond gap that you can play with, which is good because there's other sources of variability, like network latency. So these are round-trip pings from Boston to Santa Clara. Most of them fall in a very, very small window. But there are others that you have to account for. And there are a couple of ways you can think about doing that. If you end up in an interval with very low ping times, or very high ping times rather, you can just rerun the test at a later point. If you can test a nearby server, so that your data is being stored in Seattle by Amazon, and so you ping Microsoft, you can get some sense of what that cross-country latency is going to be and use that. Or you can just design enough steps into your protocol that you can overcome anything that you would happen to see. And obviously, this is suspect to how far the data is traveling. So Boston to Santa Clara, basically a cross-country trip. If you do, within the Northeast, you get a very similar graph, but everything's scaled down. And if you do Boston to China, you get, again, very similar data, but expanded. So you're looking at 700 or 800 milliseconds round trip, Boston to China. And in the Northeast, you're under 100 almost always. So that's all something you have to design in to your protocol. So, jump into the summary. PORs, as I already talked about this morning, let us efficiently test whether our data is being actually stored. To do that, you've got to have a PRP that works on any size domain. And building those for the size of files that we looked at was non-trivial. Also, that encoding must be done sequentially. The very first version tried to do random access from disk, and that didn't work at all. Hails then lets us build our own fault tolerance into the system, so we can take a bunch of cheap cloud storage providers and cobble them together into something that gives us fault tolerance. But again, you've got to pay attention to how you do the encoding if you're going to do that. This is being done on a client machine that has limited computational power, limited RAM, and so the order in which you do that encoding can actually make an enormous difference. And then finally, RAFT is really designed to allow us to test that data is being stored with fault tolerance. If your cloud provider is promising you cloud or fault tolerance, how do you actually test that? And by fault tolerance in this case, we actually mean resiliency to drive failures. However, drive caching or hard drive caching restricts our design space. The seek times to read data off of a drive and the variability you see in those enforces a necessity for a lockstep protocol that can run multiple rounds. And then you also have to account for the network variability between you and whoever you're testing. And then publications we've put out on this stuff. Questions?
So can you do it to files in a streaming model when the file comes in a stream and you want to encode it and put it on the server without doing it twice?
So in a POR, we're essentially doing a single pass read over the file. So yeah, if you can keep up with the encoding, then yeah, you could do it on a stream. Hail actually uses a 2-pass encoding, so you would have to store some temporary information to be able to do that. And the RAFT, I actually haven't thought if you could do it in a streaming case with RAFT. Probably. The encoding is very similar to a POR. It's more in the actual design of the test that you have to account for variability. So that you could probably do in a streaming model as well.
How hard is it, truly I'm sure how hard would it be for the provider to actually just add some noise themselves to the signal, basically, by either adding some jitter to the times in various locations? Can you account for that, or are you basically assuming that's outside the threat model?
So that is very much inside the threat model, is that the adversary will add noise, will delay responses in order to gain an advantage. Basically, I assume you're talking mostly about RAFT here. Yeah. So the primary assumption there is that we know what class of drives the storage provider is using. So there's a big difference between desktop class drives, enterprise class drives, and solid state drives in terms of their response characteristics. But within a class, the response times are close enough that you can do the tests assuming that you are actually getting the hardware that you're expecting. And you sort of have to go back to an economical motivation to assume that. So if they're going to promise you desktop class drives, you're going to pay desktop class rates, and they thus can't afford to actually have enterprise class drives. And same going from enterprise to solid state. So if you assume based on how much you're paying that you know what sort of drives your data are being stored on, then you can do this regardless of whether or not they're adding noise, because we have a good characterization for how those drives operate. Yeah?
So you said you permute the data using this PRP.
Mm-hmm.
Okay. I don't see why you need computational pseudo-randomness at all. Can you use a pairwise independent permutation? Because you encrypt this you permute it, you do this correction, you encrypt it anyway, so there's nothing leaking about the permutation that we use. So I don't see why you need any computational hardness there. Pairwise independent should do that.
So the reason you have to permute before you do your...
I just don't understand why you need computational hardness in the permutation. I know pairwise independence, for example.
Right, so exactly. So that's why we can go down to a Feistel construction and still achieve the bounds that we're looking for. So you're right, we don't need strict PRP guarantees, but we need to be close enough that we can claim with overwhelming probability the best an adversary can do ends up being random corruptions. And so
like a PRP with a balanced Feistel over 2 to the 25 bits is birthday bound basically is going to be 2 to the 12. It's nothing. So, but I don't see why you need a computational primitive at that point. You're permuting, and you just need this for this correction. Yeah, for this combinatorial property, I think you just need the information theoretic pairwise independence, almost pairwise independence, because you permute back, right?
Yeah. Actually, yeah, it's been a couple of years. I don't remember the motivation or the proof that we have behind it, but certainly something we should talk about offline. That's an interesting thought. Because, yeah, if we could avoid that cost, it makes all sorts of things easier.
Another question for me. So can you modify RAFT or use the kind of idea behind RAFT to do like counting of hard drives that a cloud is servicing somehow? Or alternatively, like fingerprinting hard drives, you can have enough detailed measurements of particular hard drives, like timing. So
fingerprinting would be harder. I'm not sure it's impossible. It's not something we've looked at. In terms of
layers, right? Because they might be moving things around.
Yeah. In terms of counting, that should be possible. You should be able to design the protocol in such a way that counting becomes feasible. It's not something we've done, but certainly an interesting thought.
Do you have a sense if providers are concerned about these types of things, like people being able to count their resources?
So the people, and this is all my sense on this, but my assumption would be that if you're going to advertise multiple copies, then you would be less concerned about someone actually trying to count them. And if that's something you don't advertise, then it does become an issue. Especially we get back to the deduplication question. If I've got a file that's been deduped down to one hard drive, I'm not going to advertise that to the world. So if I have somebody trying to count the number of drives I'm using, that could raise some flags.
Do you want to thank the speaker again? Okay, so last talk of the day. We got Tom Roeder talking about dynamic symmetric searchable encryption. Take it away.
Thanks. So I work in the extreme computing group here, and I like to say that our job is to take the bleeding edge and make it cutting edge. And so that's the goal here on searchable symmetric encryption. There have been a lot of searchable symmetric encryption protocols out there, including Senis and others, and we came to this with the idea that we try and make basically the product teams at Microsoft use good crypto and do interesting things with them. So we're trying to do things that people are going to use and you're going to be able to use. Before I start, I should thank my collaborators. So the theory and algorithms here was jointly done with Seni. And in terms of practical design and implementation, because we've implemented this, it's Mira Belenky, Karen Easterbrook, Larry Joy, Kevin Kane, Brian Lamacchia, and Jason Mackay. As usual, with systems like projects, we have lots of people here. So you've all seen this story about cloud backup, and I don't really need to talk about this. And you've even seen from Seni the motivation that I really wanted to give you, which is searchable symmetric encryption. But I'll say it again. So the basic idea in searchable symmetric encryption is you're storing your files in the cloud and you want to be able to search over them, some terms from those files, not necessarily to the words in a document, but maybe the artists in an MP3 file, the composer, something that you want to search on in these documents. And the real problem that's out there is that in a real file system or in a real email system, these documents change all the time. I'm modifying my files, and the thing that I've uploaded is no longer correct. So I need some way to update the index that I uploaded to the cloud. And the implementations, when we started looking at this, don't support that. There's no, say, some of them, there's just no update supported at all. And in others, there are efficient update operations, but they're not efficient in terms of their storage. So for instance, you have to store, say, size that's linear in the total number of documents times the total number of unique words across all documents. So we're going to talk about two different schemes with efficient update, and efficient both in storage and in terms of computation on both ends. And there's two ways we can do this. One is we can update one word at a time. So if you say remove all instances of the word the from a document, then you need to remove that from the index, and we can do just that one word. Another version, which may seem naively not useful at all compared to this first version, is suppose I modify a document, then maybe I'm just going to delete the old document and upload all the terms for the new document. And I'll explain in a minute why that might be a valuable way to see this problem. So the basic overview of what we're going to do is look at these protocols, and that's probably going to take most of our time. And if we end up having time, I'll give you a brief outline of the security proofs, and then talk about the implementation that we have and some performance numbers. So as a more explicit reminder of the encrypted search problem and how I'm going to treat it, the user has some collection of documents where each document D here is what I'm going to call a document identifier. And this isn't just the name of the document. You might want to keep more information than that. You might want to keep, say, a little 140-character Twitter summary of the document's contents, maybe some unique identifier, a timestamp. The point is this is going to be a fixed size representation of the document so that when you encrypt it, it doesn't leak any information about the document at all. And then the goal and what we're going to produce, and these are all for the document-based one, which I'm going to focus on in describing the protocols, search on some word will return to the user a set of encrypted document identifiers. The user can then decrypt them, read their summaries, and decide which one they want. This is slightly different than what Senny presented, right, where you get the documents back. This is more like Bing search, right? I search something, I get back a list of links, and then I click and actually go download the things that I'm looking for. Add, you want to add a document with a word set, delete a document, and then extend index. This is something that will become obvious why this is important in a second, but our indexes are padded to a particular fixed size to hide some of this information about the number of documents, number of unique words. And so you need some way to extend that once you actually run out of space. So the client's going to generate some of this information, send some tokens from these algorithms over, and then get some results back. It's the basic paradigm. Now we're basing this on one of the schemes from the 2006 CCS paper, Kurt Mulliger, Kamara, and Ostrowski. And the main idea in our slightly modified version of this scheme is that each word gets mapped to a token. I should say, I'm going to say pseudorandom function sometimes here, and I don't really mean it. Being a practical cryptographer, I always depend on the kindness of random oracles. And so this is going to be some HMAC SHA-256, really, that I'm going to be dealing with. And tokens then map to some initial position in an encrypted array, and each array, each index list entry here points to another position. So one assumption that we're going to definitely depend on in all of these protocols is a stronger assumption than is normal, which is we're going to assume an honest but curious server. So we're going to assume the server is going to follow the protocol, and we're going to assume that instead they're just trying to learn as much information as possible. Maybe there's some economic argument you can make about why they don't want to be caught, or maybe you can apply some of these protocols we heard about today in parallel to solve that other problem. So here's a modified version of the Kurt-Molla et al. Scheme. There's an index, and there are list entries. And the index then has a key that's the output of this function f, which is really HMAC SHA-256, on some key on the word. And it points to then a start position of a list of documents that contain that word. And each list entry at a high level is the encryption of the next pointer for the next element in the list under some key that depends on that word. And then it also has a second component, which is the encryption of the document identifier under a key known only to the user who generated this. So how do you do search in this context? Well, the user has a word, and they have these keys, KC, KB, KG, and they can then, for some key derivation function with KG, generate a key for that word. And then they can construct a token, FKCW, FKBW, and KW. And they can send this over to the server, who uses FKCW to look up in the index the encryption of or really a masked version of the start position, which they can then unmask and point to the first element in the list and use the decryption function to walk the list. And they get back these encrypted document identifiers. This doesn't actually reveal anything about the documents. It simply reveals a count of the number of documents. These are sent back to the user, who can then decrypt. So this is really a modified version of that scheme. Now the question is, how do we do update? Well, the problem is we need to change these lists over time. We've changed a document, so we need to change the list of, we need to add that document, say if we've added a word to that document, we need to add it to one of the lists. But all the pointers in our lists are encrypted. And we don't really want to go giving away key KW, the key to that list, every time we want to change it. Otherwise, we'd be revealing every document, or at least the count of documents for that word. So instead, we're going to depend on this honest but curious assumption and choose a particular implementation for our encryption scheme, which is this simple mask of a stream cipher, effectively. So you have a random value, and then the pointers for the previous value and the next value masked by f sub kw of r. Right? So suppose you want to remove x from this list of pointers. That's meant to just be grouping. There's no inner product, nothing. This is just brackets. Yeah, you got an issue. Yeah. So suppose from the server can get p and n, and we'll say nx so that it knows which one to delete. It's really easy to change this, right? It can XOR 0, x XOR n, and x XOR p0, and XOR them against that piece. Since XOR is commutative, it changes it under the encryption, and now you've pulled out x. Right, so it's a simple trick. How does the server get its hands on p and n is the real question. So to do that, we're going to add a new data structure. And it's basically going to be a mirror image of the data structure we already had. So our old data structure mapped words to the documents that contain those words. The new data structure is going to map documents to the list of words in that document. And it's going to contain for each word the pointer to the position of that word in its list and the pointer to the previous and next values in the list, and a little bit of bookkeeping information that you can see in this overly complex specification. So let's look at it in a picture. So here's the original list that we saw. Here's our new data structure. This orange bar is the deletion list entry for this, I believe, as we'll see in a second, entry in the list. And it points to x, and it points to the previous value and the next value. It also, of course, is a list, so it points to the other words in this document. And finally, notice that this deletion entry contains pointers to previous and next for each word entry. So we have to patch the deletion list entries when we patch the entries in the other list, too. So additionally, this deletion list entry also contains a pointer to the deletion list entry for n and a pointer to the deletion list entry for p, so we can patch those at the same time. But all the patching is done according to the simple XOR trick. Okay. So there's still something missing, which is we need some way to be able to keep track of the empty space in this padded index. In the original scheme, you generate these lists, and then you just pad the list with randomness. And the problem is if you need to add something to the lists, you need to know which space isn't used so you can get that space and add it. So the simple and perhaps obvious solution is to encrypt the list of entries, of free entries. We'll encrypt the free list in this index. But we can't just use the simple encryption that we used before, right? Remember that for words, we encrypted them with a key that depended on that word. So if we did that for the free list and we just had a single key for the entire free list, then we would give that to the server when it needed some information, and it would decrypt the entire free list and learn all that information that we were trying to hide as soon as we added a single document, which would defeat the whole purpose. So instead, we have a unique token that maps to the free list. This is uniqueified, so it's not really exactly that. And so you can still search on the real word free list. It's some list, and each of the main entries also points to a unique deletion list entry. Note that there's a one-to-one mapping between used main entries and used deletion list entries, because each deletion list entry is set up for one main list entry. So you can also set up a one-to-one map for the free entries, and you can just keep track of them with a single list. So instead of keeping a single key, we just use some more masks. This entry contains a pointer to the next entry. It also contains a pointer to the current deletion entry, and it's masked by the output of our HMAC on a new key with its position in the free list. So that means that the user can dole out just enough free list tokens to give space as needed for add, and this doesn't actually for add and delete operations. So this doesn't asymptotically change the cost of tokens sent over. There was already a constant amount of information that needed to be sent for each word that was changed. We're simply adding an extra bit of information that needs to be sent, which is the this mask value. Now, there's one thing that does change significantly because of this, though, which is that the user now needs to keep track of the current count of the free list, because otherwise it won't be able to produce the correct tokens to decrypt the free list. So this makes the protocol stateful in some sense. You can still have other users search and give them their key, but if anyone wants to add, they have to coordinate and they have to keep track of this bit of information. So given all of that, let's see how to add a document. Here's the full data structure with main and deletion, our deletion index and our main index. And the user generates a set of tokens as written at the top here. So it adds a doc token that is what's going to be added to the deletion index. And it also gives free list tokens so that you can find the free list and move it so you can get the top entry. And then it provides some templates that are the partially filled out main and deletion list entries. And it provides a word token for each word so you can find the list, the server can find the list, and then does the patching trick to put the word on the document on the front of that list for that word. And deletion is similar. So the deletion token is somewhat simpler. All you need is the document token, the doc key, and some free list tokens, right? So there is the document token that lets you find the deletion list entry, and the main list entries then for that entry, which are part of some word. And they have their own corresponding deletion list entries. And then you perform patching. So given this entry, you have enough, the server has enough information to patch around and to patch the deletion list entries and patch it out and turn it into a new free list entry at the top of the free list. So these are all very efficient operations. This is mostly computing a couple symmetric operations and doing some XORs. So finally, index extension, which is trivial. Given that you've filled up the list or you want to add more elements to the list as the user, you can encrypt a set of free list entries and permute them into an array that's just a block and send it over to the server. And then tell the server, okay, here's the new top of the free list and here's the bottom of the free list so the server can patch it back in to the old top. And you end up with an identically looking array. So that's the document-based scheme. The word-based scheme is almost identical. So I only need one slide to say it, given what we've said here. The only difference is, since you're changing one word at a time, you don't need to keep track of lists of words for a given document. Instead, you map in the index, you keep the key as a key on the document identifier and the word concatenated together. And then keep, again, track of the XPN values, and now the index keys instead of the positions in the list for the other deletion list entries. And you can perform exactly the same algorithms given this structure. So why would you use one of these over the other in actual practical terms? Well, what does word-based update buy you? The nice thing about word-based update is the cost of your tokens is linear in the number of words that you're changing. Whereas the document-based scheme, the only way to change a document is to delete the entire document and then add a new document with all the terms in it. So this may seem totally useless, but the value of the document-based scheme is that you don't have to keep state on the user's machine, except, of course, for this small piece of state that's the free list. So if you're actually implementing the scheme, when you do word-based update, you have to keep track of the diffs every time you modify a file. And so there's a lot more work to be done on the user side. So actually, in our implementation, we currently use document-based update. OK. So I'm going to briefly touch on the outline. What? Oh, it's time. So I'll briefly touch on the outline of the security proofs. The basic idea, I think, was presented by Seni, which is you have this fairly large number of algorithms. so key generation, the index generation, each of the trap versions generates the token. So trap S for search, trap A for add, trap D for delete, and then search and extend index. And the adversary has to distinguish between two scenarios. So one in which it's interacting with the SSC protocol, and another in which there's a simulator and it's interacting with this random oracle that the simulator actually programs. So I'm only going to show you how to write the simulator. It's really straightforward. The simulator doesn't have any information. So as usual, the simulator is just going to make almost everything up. And the only trick is how the simulator programs the random oracle. And the one thing I didn't draw in this diagram is that there's some sort of leakage. So Senny already talked about the query and the access pattern. The query pattern is you're leaking some unique information about the things that you're searching. And the access pattern is really which documents then are retrieved. Our algorithm, of course, leaks somewhat more. So it leaks this update pattern, which is it leaks unique identifiers for every word that you add for each document. And those identifiers can be correlated to the query pattern, so you can tell that you've added to something that you've searched before. And it leaks some information about the free list. So it leaks when you reach the bottom, it leaks the tail of the free list. But given this, it's straightforward to do the simulation. So index generation and index expansion, the simulator just generates large random arrays and keeps track of them. The search is the same as in the original paper, but I'll say it briefly here. So what gets leaked in our version of the search protocol is the number of results that you get returned, because we actually return just an set of encryptions for the document identifiers. So what the simulator does is, if it's seen the search before, fine, it's easy. Otherwise, it chooses random entries in the array and chooses a random index entry, and then produces for its token masks that will first unmask the index entry to point to its first starting point of the random entries, list entries it chose. And then it programs the random oracle like this. So suppose it wants to end up pointing x at a next value n. Well, it programs the random oracle, says if you see the kw, which is a random value I generated, and r, then generate this value, which is pn XOR r prime. And then when the adversary queries the random oracle for these values, it ends up decrypting just to the pointers that are necessary. Similarly, add and delete are straightforward. Add chooses random values to add and doesn't need to program the random oracle in any way. It just chooses masks correctly. And deletion is given the unique IDs of the deleted words. So it, again, gets to choose some random key, k sub d, and programs the random oracle on that key so that it decrypts the deletion list correctly to point to the random values it chose. So these are straightforward, if somewhat complex given the data structures. Okay. So we've implemented this. This is an implementation in C++ over an Intel Xeon x64 over Win 2008 R2. And the test here, so some of these results are highly dependent on the particular distribution of words that you have, because there's some overhead in, say, adding a new list versus adding words to that list, or adding a new document as opposed to adding words to that document. So the way we did this is something that we hope is reasonable with respect to normal distributions of documents, which is what I'm going to call a double ZIF distribution. So we have a distribution of 10,000 documents, according to ZIF, and 500,000 unique terms. And the way you generate your pairs is you draw a document from your ZIF distribution, and then you just draw words until you add a new word that that document hasn't had before. So what this basically is doing is writing the documents on the fly, according to the ZIF distribution. And we end up with 250,000 unique document word pairs for this test. So we did it 50 times. These are the sample standard deviations, is what the plus minus is. So in this case, index generation per document, unique document word pair is 88 microseconds per pair. So this is something you can sit and wait for to finish. And if you're running it on a server in the middle of the night, it wouldn't hardly be noticeable. Search per document, and this is searching on the largest document in the ZIF distribution, is 3.2 microseconds per document on the server. Add has a dual cost, both add and delete, because you have to generate these tokens. So add has more cost on the client side because you're generating templates that get inserted. So it's 38 microseconds on the client and 2.1 microseconds on the server. And then delete is the flip, because deletion, most of the work is done on the server side. But these numbers basically show that it's easily efficient enough to be used in practice. And we have an implementation built over Windows. So this is a straightforward, obvious implementation perhaps. But there's a backup service that runs, and it has a key manager and some indexer that hooks into the Windows indexing service, so that anything that can be indexed by Windows just gets the terms out of that indexer and passes it into SSE. And then it generates tokens to send to a remote foreign server. Maybe it's in the cloud, maybe it's some server, say, run by someone else in your family, somewhere across the continent. And it just performs this remote backup. And every time a file changes, the Windows indexing service picks up those changes and passes it to the SSE algorithm, which can generate the tokens to get sent over and do update. And so searches can be performed, again, across this connection. I mentioned the Kurt-Mola et al. Scheme. This other scheme that we're closely related to here is Sedgwick et al., which has an update mechanism. It's the only other SSE scheme I know that has an update mechanism. But their update mechanism basically has a bit pattern for each of the documents that's under an XOR encryption. So that's what allows them to do the update, as in our scheme. But since they're using this bit pattern for the documents, they have to have a bit for every document that is stored on the server. And so that's significantly less efficient in terms of the actual storage costs. So I've shown you a couple of dynamic SSE algorithms, practical implementation, and they support the add and delete operations that you actually need. And I've shown two different versions of them, which you can then trade off, performance versus leakage. Thanks. Time to go.
So you have this honest but curious assumption, right?
Right.
And there's no way to tell the exact deviation from the protocol on the server end?
Right. Basically, if you have a malicious server, they can give you the wrong results. They can. What they can't do is yeah.
Confidentiality. Though, I mean, they can. I mean, how easy is it to break the scheme?
I don't think they. Yeah, they can't break the confidentiality. I don't have a proof for that. But I don't think that a malicious server can break the confidentiality, given that it's masked with random values for keys that it doesn't know, and it's unique values because of the randomness for each of the chosen masks.
So in terms of confidentiality, what assumption would be broken by deviating from honest security?
So actually, it may be that a malicious server can learn more about the distribution, so get more leakage from your system. So for instance, if they can send you messages, if you're encrypting email, they can send you an email that says cryptography, right? And so if you index this naively, then they're going to learn some information about, well, maybe this is cryptography, all right, this particular piece.
Sorry, can you speak out?
So the security definitions account for these types of attacks, where the adversary can choose the queries that you're going to, or the data that you're going to query,
yeah.
and that you're going to query. So with the caveat that you're leaking the access pattern and all this stuff, then that's sort of taken care of. The malicious adversary could, I mean, the honest but curious sort of assumption is there for correctness, essentially. We don't necessarily know whether you're getting the right documents back.
Which is detectable. Oh, so that's not detectable necessarily, because it could be. But you could think about trying to test that.
You can check availability. I mean, you can test that you're getting true documents back, right? Because you could use an authenticated encryption scheme, for instance. But you can't tell that they're the documents for that word, right? Because he could just pick arbitrary document identifiers.
But you can test that by keeping a local cache.
You can't test completeness. You can test that if you decrypt your answer, you can see that your keyword is contained in the documents, but you don't know if all the documents that contain that keyword were there to you.
That's the other problem, yeah. That's the other side of the availability.
Ideally, you would want to be able to test this without even encrypting all the documents first, right? You want to just like assure that everything is encoded. You verify that, and then you decrypt. Just so you don't have to waste time.
Any other?
I was wondering about the space complexity. So basically, you said that whenever you delete something, you keep an entry in this free list, if I remember correctly, right?
So when an entry is deleted, its space is returned to the free list. So I don't keep extra information for things that I've deleted.
Okay, so you don't keep any pointer to some entry in the free list whenever you delete something?
No, the space for the thing that got deleted is then returned to the free list to be used for other things. So that just recycles the space.
So,
Yeah. Yep.
So the numbers you're getting for sort of normalized per sort of pair of
Right.
things, do you have just a ballpark of like sort of a macro?
Well, so yeah. I mean, for the particular, I mean, you can work it out, right? But the number, so you can see it takes, what would it be, like 250 seconds, approximately, a little bit less, 200 seconds for the encryption of the particular example that I had, generating the index. And then the add and delete are basically unnoticeable, right? Even with this distribution, you have some thousands of files, but they only take, 3 microseconds each on the server. So it's just not a noticeable amount of time to do those operations.
So at what scale does this does it start getting too slow?
I mean, you'd have to be up at the, for add and delete, you'd have to be up at the hundreds of millions of entries. And at that point, your network bandwidth is what's going to kill you. Sending the tokens across is going to be much, much more expensive than the actual computation. Yeah.
Any other questions? Great, let's thank all the speakers.